doing?
Yeah, visible.
Yeah. Okay. Last class we talked about bunch of problems related to linked list. We have gone through, a couple of problems. These are the list of problems we have discussed. Do you have any doubts? Okay, fine. Today let's talk about trees. Trees is the next set of data structure. Okay. If you compare to the in the previous topic we had talked about linked list, right? Linked list had two parts. One is the data part and the other one is the link part, right? See, this is the each node have some kind of a link, right? So it had each node had two parts. One is the data part, one was the next part. Next part would contain the address next node. Say this is node A, this is node B. And if you look at the next version of single list, list, whatever we had discussed, is a doubly linked list. It had a two pointers basically. Instead of having only a data and then next part, it had three parts. Each node would contain three parts. One was the previous, which contained the pointer to the previous node. The other one is the data part, which would contain the data. It could be int, it could be float, or it could be class object or whatever it is. And then the next pointer would contain the address of next element, right? And then the previous of next element would contain point to the current element, and the prev of current would point to the previous element, and so on. You can, if you look at the tree, you can somehow you can compare to the doubly linked list. Trees also has three parts. One is the data part. Okay, you can compare whatever the data it is, and then it has two pointers. One is the left, and then other one is the right. You can visualize something like trees here. I mean, if you look at it, when we were discussing priority queue, right? Priority queue, why the conceptually we have to think in terms of trees, right? So trees, what is the left child, what is the right child? How do I calculate the parent? How do I go to the parent? How do I come to the left child, right child, and so on? All these topics get discussed while talking about heap. So even the tree this is basically a binary tree. Binary tree means it would contain, data part, left child and right child. Left child would point to the left child node, and then right child would point to the right child node, and so on. Assume I want to insert say 10, 20, 30, 40, and so on. So many elements I want to represent in terms of tree. See, if there are any constraints, we can apply those constraints while constructing the tree. If it is a random numbers and I can construct a tree like the way I want, I can construct like anything. Say 10 is my root, insert 20 to the left, insert 30 to the right, and then 40 to the left, and so on, whatever the way. So if you look at it, it looks like a tree, right? This is the root, and this is the left part of the subtree, and this is the right part of the subtree, and then this is left child, and then it has again left child and right child. Basically, the binary tree would contain the data part, left child, and then right child. Left child would point to would contain the address of the left element, and then right pointer would contain the address of the right element. So this is the binary tree, and there are various trees like binary search tree. Binary search tree is also, you can think of a tree, binary tree. That means it has a root would contain the left child and right child. But here the constraint is, if I have the root element 100, right? If I want to insert 500, so you have to insert based on some constraint. So the constraint would be something like the left element, left subtree should be less than or equal to root, or less than, you can think of, or right subtree should be greater than root. That means these conditions we have to apply. Need not be the same. We can interchange the version also. Either you can go all the lesser elements to the right side and then or bigger elements to the left hand side. But by convention, whatever the elements which are lesser to the root goes to the left hand side, and then whatever the elements greater than to the root goes to the right side of the subtree. So if you assume I have 100, and then if I want to insert 120 and then 50, I need to apply this condition before insertion. So since 120 is greater than 100, 120 will go to the right part, and then 50 is less than my root, it goes to the left of the subtree. What if I want to insert 80 after inserting 50, right? Okay, let me erase this. So assume I want to insert 10, 8, 20, 15, then 13. You can think I'll make 10 as a root, then I need to insert 8, check what is the value of 8. 8 is less than 10, so I insert 8. Then come to the 20, parse 20, and then compare 20 against 10. 20 is greater than 10, so 20 you inserted the right part. Again, parse 15. 15 is greater than 10, so it should go to the right part. Then compare 15 with 20. 15 is lesser than 20, right? So it has come to the left side of the 20, so 15. So then 13. 13 also greater than 10, it comes to here. We can apply the comparison here. 13 is less than 20. So again, apply comparison here. 13 is less than 15, you can insert 13 here. So what if I want to insert 9 after this? 9 is anyway lesser than 10, so it comes to the left at this point. So again, you can apply the comparison. 9 is greater than 8, so you can insert 9 at here. So this is the basically a binary search tree. Okay, so what is the advantage of binary search tree, right? So the advantage of binary search tree is, say if I want to search 8, so here only I will check whether 8 is greater than 10 or less than 10. If it is less than 10, I process the left subtree. If it is greater than 10, I process the only right subtree. That means one part of the subtree at one level, at any given level, I completely ignore, right? Because there is no point in going right and search for 8. Or again, assume I have so many elements, 8, 3, maybe 7, and I want to check 7. So 7 I'll check, I'll entire skip the right subtree of this part, and then I'll check whether the 7, while searching 7, I'll compare the data of 7 with the left child of 10. So since 7 is less than 8, again I skip the right part of the subtree. That means at each level, I'll skip either left or right part of the subtree based on the value. So that means here, if you look at it, the search complexity would be, the average search complexity would be log of n. But what is the disadvantage of the binary search tree, right? Assume I want to insert elements which are there in the sorted order. Say, assume I have a 5, 6, 7, 8, 9. So if you look at 5, and then so 6 is greater than 5, so it would go to the right part of the subtree. And then 7 is greater than 5, come here. Again, 7 is greater than 6, insert at this point. 8 will come here, and then 9 will come here. If you look at it, this tree is not at all balanced, right? It is the growing towards only one side. So if the data is in sorted order, either left, it could be sorted in the increasing order or it could be in the decreasing order, right? Either in that case, it goes either right side or left side. It's getting recorded, right? Yeah, sorry. Yeah, either right side or left side. So that means we won't be accomplish the search complexity with log n, right? If the tree is constructed in this way, so the search complexity, worst case search complexity would be under O of n. So which we don't want to do O of order of n, because we should bring down it to O of log n. So in order to do this, we need to alter the binary search tree. That means if the height is not balanced, say for example, I need to identify at this point in time, okay, if it goes one level above, that is fine. Say assume I have a 5 and then I inserted 6. This is fine because only left subtree doesn't have anything, but right subtree has only one value. But again, if I want to insert 7, so it's the value of number of the child 5 has left child is 0 and the number of right child is 2. That means it is going beyond 1, right? So here there is a room for improvement. That means can I balance it somehow? So yeah, I can balance it somehow, do something like 6, 5 and then 7. That means you do one round of a rotation. from year to year, make this guy root, and then make 5 at the left hand side and 7 at the right hand side, so that tree gets balanced. So let's talk about all the, how do we balance the tree if it is not balanced. That means, so that at any point in time, if I want to search any value, I can accomplish search with the order of login. So this one I would like to cover in detail while covering either red black tree or the avial tree. That will cover a bit later after we, and after we understand the binary tree, binary search tree, and the basics of the tree thoroughly. So I'll not jump into the red black tree or avial tree today. Maybe once we today and tomorrow, let's talk about the fundamental, binary trees, binary search trees, and how do we insert, how do we search, and we'll discuss a couple of problems in this area, and then we'll jump to the height balanced trees. So far, any questions? No. So then, what are the real world applications, right? I have noted down some of the applications here. See, if you look at the DNS resolution, right? That is also okay. This, yeah. If you look at this, is the root level, and then we have a .net, .org, .gov, .com, and so on. See, this is the whatever the tree I discussed is a binary tree, right? So, but tree in general, tree need not have only 2 pointers. One is the left and right. I can have n number of children. That is a n array tree, right? One parent can contain any number of trees. That is also possible. So the n binary tree is just subset of a tree. So what are the real-time applications? See, while doing the DNS search, the DNS hierarchy is maintained in terms of a tree only. If you look at the diagram here, that is the root level, then .net, .org, .gov, .com, and so on. These are all the first level domains, guys. And the next level, whatever the domain, it could be LearnBay, it could be Google, it could be whatever it is. Correct, right? And then these are all the subdomain. This goes from, this is the root, and then it grows downwards. If you look at, let's say, www.google.com, right? Say this will be the www and then Google and link. That is how the resolution happens. So this is the high level domain. Under this .com, there will be a hell lot of subdomains. I mean, whoever wants to buy a domain, then I need to buy whether it under .com or .gov or .org or .education. If it is related to education, there is one more domain called .edu. We need to buy a domain under that, first top domain, and then create our own based on our purpose. I can create the domain, and then under that also I can create so many subdomains. So this is the this is also implemented using trees only. And again, if you look at the other okay, sorry, this is the binary. I wanted to capture picture some more binary data. Fine. So then if you look at the file system, right, and then even if you look at the Unix file system hierarchy, it is something like slash. It starts from slash, then you slash from slash, and then I can create under slash. I can create directories like whatever directories, ABC, XYZ, and then say test directory, and then dev directory. Under dev directory, I can create a DSA directory. Under DSA directory, I can create Python DSA. Under that, I can create stack, queue, and so on, right? If you look at it, this hierarchy is also based on the tree structure. The first is the slash is the slash file system, and then under slash, I created a dev, under the DSA, under that Python DSA, under that stack, queue, list, and so on. And then under that, the leaf, what are the leaf nodes? Leaf nodes would contain the files. See, under stack directory, I created like inorder.py, postorder.py, or infix to postfix.py, then whatever the stack problems we discussed, right? And similarly, tree, traversals, then all the tree problems. So this is all the entire file system implementation is done through using trees. And what are the other applications? Yeah, if you look at it, you would have, if you use any programming language, if it is C++, R, Java, whatever it is, in at least in C++, STL, we have like map, and in Java also we have hash map, and then in Python we have a dictionary, right? All this dictionary implementation, map or hash map implementation is done using one of the variant of the tree. Either so that will be definitely a height balanced tree. It could be AVL or red black tree. So they use those kind of trees to implement map or hash map, so that the complexity, search complexity, would be order of log. So, and also, you would have used the database, right? It could be any relational database or NoSQL database. You take any database, it could be Mongo, it could be SQLite, it could be Postgres, or whatever database it is. But again, in database also, if you want to fasten your search, right, you need to do some sort of indexing. So that means based on that particular index, if you search, you will get the search complexity would be log n. So that database indexing also, uses the tree data structure for indexing. And also in that HTML tag implementation, right? HTML tag would contain head, body, and so on tags. So that also implemented using tree, and also XML parsing. All those things is used. It internally uses tree only. Tree are variant of trees. And again, try. Try has a very good, a good number of real-time applications. If you look at it, if you take any editor or if you or if while doing composing an email or inside the Word, editing the Word document, if you make any mistakes, right, it says if you do spell check, it does a spell check, right? I mean, while on the fly when you're writing the sentence or word. So that one is also implemented using try. Try is a variant of a tree again. That maybe we'll discuss try soon after understanding trees completely. So even the autocomplete feature, you can say in Google, right? You can if you search anything, if you say learn bay or leetcode, it is giving all the around 6-7 items, right? See, this is autocomplete. Whatever the sentences I had searched previously, based on that, it picks top n element and then it shows. The autocomplete also is implemented using try, and again spell checker, autocorrector, it's a using try only. And again, if even dictionary can be implemented using try. Say, if you look at a dictionary, how what it would contain a dictionary, right? Say the dictionary would contain the word and the meaning of the word. The value is meaning of the word, right? Say for example, my word is ABC. I want to give the value for ABC is something like XYZ. The meaning of ABC is XYZ. You can think. What we can insert is at the root. This is my root, and then I can have, since the dictionary is Oxford Dictionary would contain only the English letters, right? It could be A to Z smaller, or it could be A to Z capital. Maybe we can make it case sensitive and then create only 26 pointers. That means this parent root would contain 26 pointers. That you can map it from A to Z. This could be A, this could be B, it could be C, and so on Z. See, A, from root I can go to the A, and then here also it would contain, say, so many A to Z. From here you go to B, and here also it would contain this is A, this is B, this is C, and here it could be C, right? That means I traverse from here to A, and then here to B, and then here to C. At this node, I can mark, that means this is the end of the word. I can put a flag like end of word equal to true, and what is the meaning of this particular word? Say I can fill the value is XYZ. Here, if I want to search ABC, the order of complexity will be length of the pattern. This is also super efficient, right? So I just A, I, B, C. This is not even log n of the complete tree. Assume if I build a tree with some 10,000 words, and if I want to search that with log n, the log n is good, I understand. But if it is a constant like the length of the pattern, it is even more good, right? So probably we can implement our own dictionary by using a try data set. That is also we can try in a class, or we can take it as an exercise, which is easy to implement. It is not that difficult. Maybe I'll talk. We will discuss this one while discussing a try topic. And there are a lot of applications in tree. If you look at the compiler generates the symbol tables, right? So during compilation, during evaluation of expression or whatever it is, while constructing the symbols, that also uses a trees. And then there is a suffix tree. Again, if with all the pattern search, efficient pattern search can be, done using suffix tree. This is also variant of a tree. And all the routing algorithms, shortest path algorithm, or it is a, a BGP, OSPF, all those routing protocols internally uses try data structures. Again, graph is a variant of a tree, and graph has enormous, real world applications. So tree is fundamentally, it's a, it has a hell lot of applications. It need not be a plain binary tree, but the variant of a tree, like it could be trie, or height balance tree, or binary. In sometimes it's a binary search tree, has, very lot of good number of real time applications. So any questions? If it is clear, the theory part, we can jump into the technicality of tree. How do we represent tree? How do we insert? How do we traversal? How do we traverse? What are the various traversal types?
Yogesh,
What is
one
it?
question.
Yeah.
That hash map is also internally implemented as a tree, is it?
Yeah, that is, there are two. It depends. A tree only, definitely.
Okay.
It could be AVL tree, or it could be red black tree. The hash map is using red black tree only. Map is using implemented internally using red black tree.
Oh, okay. Okay. Okay.
There are, the only thing is, even if it is a AVL tree or red black tree, there is a little difference. See, one of them makes insertion is bit costly and search is efficient. The
Okay.
other one makes search is bit costly but insertion is efficient. See, if I'm inserting all the elements only one time, and I'm okay to have my insert to be costly but search needs to be efficient, in
Okay.
that case I can pick one. Or if I'm on the fly, my goal is to insert a lot of elements, I need to pick the other one. So I need to consider before choosing which one, based on the requirement.
Okay. For which one is that insertion costly, and for which one it is that
I
search?
think red black tree insertion is costly, search is login.
Okay.
For the AVL, insertion is login, but search is bit costly. I'm bit confused, maybe
Okay.
one of them is yeah, I think AVL tree is if you want to search, make it search fast, I think you should use red black tree, otherwise AVL tree.
Okay. Okay. And that's like a trade-off, right?
Yes,
Search versus insertion.
yes, exactly. Yeah.
Okay. Okay.
So, and again, if we understand tree good, right, then probably it will be easy to understand all the graph related problems, because again, a graph is a variant of a tree. Here, I'll have either only child would contain 2 pointers, one is in the binary tree, but in the graph, I'll have a number of nodes, and then I can have a number of edges. I mean, all the nodes are pointing to all other nodes. It's a kind of full mesh. So, it will be easy to understand graphs also. So it's a good data structure to learn. Again, today let's jump into the technicals of tree. As I told, it would contain, in case of a binary tree, it would contain, one is the data part. This is the data part, I can call it. So assume 10 is a data part, and then it will have 2 pointers. This will be the point to the left child, and this will be point to the right child. And I can store 8 here, and again it will have, and I can do, this is the left. If nothing is there, it will be null, and then if nothing is there, it will be something like null. And again, if I want to insert 100 here, I can insert 100 here, and then this will be null, and then this will be null. Say again, if I want to, again, this is a plain binary tree. And see, binary tree, how many numbers, in case of binary tree, how many number of nodes I can have, right? Say here also, assume I have, the level is at 0th level, I can have only one node, because the only root can exist at the 0th level, right? And what is that first level? I can have two nodes. This is one and this one. Here, maybe I say assume I have some, 101, 102, 103, and then 104. I'm not following any order here, something like binary search tree or something like that. Just randomly I'm inserting. It is a just tree, binary tree, not binary search tree. At this level, second level, how many number of nodes I have? 1, 2, 3, 4, right? So this is 1, 2, 4, and again at the next level, this will be two nodes here, two nodes here, two. That means 8 nodes. If you look at the pattern, 1, 2, 4, 8, 16, and so on. So that means if you look at this, this is a 2 to the power of 0, right? 2 to the power of 0 is 1. This is 2 to the power of 1, and this is 2 to the power of 2, and so on. So if the level is 3, 0, 1, 2, that I'm starting indexing from 0, so it is 0, 1, 2. The total number of levels are 1, 2, and 3. 3 levels, right? How many number of nodes I can have? This I have 1, and this I have 2, and this I have 3, right? That means 6 and 7. If you look at it, this is something like 2 to the power of n minus 1, right? That means 2 to the power of 3 is mm, this one, right? Not this. How many I have? 1, 2, 4. Yeah, 2 to the power of 3 is 8. 8 minus 1. That means 7. Correct, right? So how many number of I can hold if I fill all my binary complete binary tree? It will be 2 to the power of n minus 1. And in the next level also, if I this is the formula we can derive, right? This is the 0 and this is 2. I mean, zeroth level it will be 2 to the power of 0, 2 to the power of 1, 2 to the power of, I mean, so on. So if I want to calculate the total possible number of nodes I can have in the binary tree, it will be 2 to the power of n minus 1. So any doubts? And again, if you look at how do I calculate the height, see this is the height of this particular thing is the maximum depth, right? The what is 0, 1, and 2. So this is the 3 nodes I can have. Yeah, we'll understand once we start solving the problem here. So
Okay.
yeah.
Yeah. So remember you gave one example of unbalanced tree, like the data is sorted and then you go only in one direction, maybe left or right. In that case, you will have more levels. Like you will have, like in this case, let's say you have only 3 levels, but if the data is sorted, then you can have maybe 5 or 6 levels. Does
Yeah.
that change
The levels will be number of nodes. Yeah. If you have inserted 10 elements, it will be levels will be 10 levels. Yeah. In that case. Hello. Hello.
Yeah, the 2 to the power of n minus 1, that will still hold the unbalanced tree as well, correct?
This one, no, this one, this is, okay, this formula is in case of a binary tree, if I want to fill both the left and right part correctly, the how many possible number of nodes I can have. This is not something like what is the height of the tree or what is the level of the tree. The formula is not for that. This is this many number of nodes I can have, maximum number of nodes I can have, but given the some levels. See, if I'm defining my level of the tree, height of the tree is 3 levels of nodes I want to fill. Total possible number of nodes is 2 to the power of n minus 1.
Oh, I see. So you are defining the height first, meaning the level first. Okay, I want to have a 3 level or 4 level.
Yes.
And what's the? I'm just jumping ahead. I mean, what is the reason why would we define the height upfront?
No. Just randomly, I'm telling. See, if my level is, if I want to fill 3 levels of the nodes with the 3 levels, how many possible number of nodes I can have?
Okay.
The upper limit. Just I'm how to calculate the upper limit. That's all. Is it clear?
Yogesh, does it mean that the number of levels we would already know pre-hand? Is it that we need 3 levels and we have to then fill, uh, like we can then fill these many number of elements?
No, no. This is something like, okay, maybe yeah, we can do that only in case of height balanced trees. In case
Okay.
of height balanced trees, see if you look at this example. I mean, I'll take one. No, that one just I wanted to tell how many possible number of nodes can exist if the level is given. That is the that point only I wanted to convey here. So,
Okay.
but
But
for
in
to
during
answer,
the construction of the tree, we don't initialize the number of levels and all
no,
that.
no, no,
Okay.
no. Dynamically, we insert into the tree.
Okay.
We don't
Okay.
consider level. But
Okay.
once the tree is constructed, I can figure out what is the how many levels depth it has, and what are the leaf nodes, and because I can traverse either depth based or breadth based, and I can find out all these elements. But
Okay.
yeah, but while constructing, we don't deal with levels.
So it's like post calculation kind of thing
Yes,
after
exactly.
construction.
Yeah,
Okay.
exactly.
Understood.
But during construction, say for example, if it is in the sorted order, the tree would go towards right hand side or towards left hand side, right? If it is a 10, 20, 30, and so on, if I'm constructing a binary search tree with the constraint that if the elements are greater than root, go to insert at the right. If the elements are lesser than to the root, go and insert at the left hand side. If that is the case, and if the input is sorted order, either the tree would go towards right or left.
Okay.
So that is the disadvantage, right? If
Yeah.
I do 10, 20, 30, the left part will have only null nodes, but right hand it will have only the nodes. But
Okay.
here, if I do search 40, the complexity will be order of n. But my goal is to have the search complexity is log n, because I can use linked list only, right? If I want to
Yeah. Yeah.
have,
Yeah. Correct.
because
Correct.
linked list also I get order of n complexity worst case. But
Correct.
there's no point in having binary search tree if I'm maintaining only one order. So in
Okay.
order to overcome this problem, I can use variants of height balanced trees. It could be AVL or it could be red black tree.
Okay.
That anyway, I'll come to them a bit later.
Okay.
How
Okay.
it works in case of AVL tree or red black tree is, consider I inserted one, so the tree is empty. I can make my one as a root,
Okay.
and again I inserted 2. So check whether a 2 is greater or less than 1. It is greater than 1. I inserted a 2. This
Okay.
is also fine because left node is empty, but
Okay.
right node is having 2. Because it's possible, right? If I have even number of nodes, I can't fill all the levels.
Yeah. True.
Again, I inserted 3, but by looking at the convention, 3 will go here. But I can insert 3 here. But if you look at it, it is it's not balanced, right? The height of right, and
Yeah.
then if you look at the height of the left subtree, height of the left subtree is 0, and the height of the right subtree is 2, because it has two nodes, right?
Okay.
So
Okay.
this is a bit imbalance. So
Yeah.
what I can do some kind of rotations based on some logic. So
Okay.
assume I did a rotation something like left rotation, or some I did rotation. So in that, as part of that rotation, I make 2 as a root, and 1 as a left child, and 3 as a right child.
Okay. Okay.
Correct, right? Now it became balanced.
Yeah. Yeah.
So that means as and when the balancing goes out of order, keep balancing it.
Okay. And this is AVL tree concept, is it?
No, yeah, AVL tree also we do left rotation, we do right rotation based on some
Okay. Okay.
permutation and combination.
Okay.
Uh,
So this is just to counter that left heaviness or right heaviness, right? In the
exactly. Yeah.
okay. Okay.
Uh,
Understood.
Zoom ID or the
But
Abhishek.
in does the ordering of the like in this case, right?
Yeah.
You guess 1, 2, 3. We rearrange to 2, 1 to the left of 2, and 3 to the right of 2.
Yeah.
What is the ordering of 1, 2, 3 in this case that cannot be changed? Meaning, is there a 5? This doesn't have a FIFO method, meaning first in, first out, or the last in, last out, last in, first out kind of a restriction.
No, it doesn't have those kind of things, like we need to have either first in, first out, or last in, first out. It's something different. See, your question is something like, do I need, what if the constraint is the root should be fixed? Something like that?
Yeah, basically, see, we have a list of 1, 2, 3, or let's say 10, 20, 30, where we cannot we cannot change the order of the elements arriving, right? So the first is, so, but here by doing this, you are changing, it looks like the 2 is the top root, and then the second node is 1 and 2.
Here, during insertion, I'm doing all these things. Once my insertion is complete, kind of root is kind of fixed, right? So this is, I'm doing for some purpose. Like if my goal is tree should not go out of order. That is the only constraint. So that has a different set of applications. Like, I can, by doing this, I can make the search complexity, I can bring down the search complexity to the login all the time. I can guarantee that. Maybe we can come back to this, the aviary tree. I'll implement and show what are all the different rotations we need to make, and how do we guarantee the search complexity to the login. What is costly? Your insertion is costly, or search is costly. We can discuss in detail. Maybe it takes another, maybe half of the session to talk about the aviary tree. The only thing is, at the very beginning, I didn't want to jump into the complex part of it, because I wanted to explain from basic, like what is a tree, what is a binary tree, what is a binary search tree, then play around with some problems, and then jump into the tree. Probably tomorrow or next week we'll talk about binary, sorry, height balanced trees.
Yeah, that sounds good, Yogesh.
Okay. Any questions? Fine. Then let's talk about traversals. Okay, assume I have a tree. A tree is given here. You can assume I have a tree with 100, 200, 300, 400, and then 500. See, the root pointer is given. This is the root, and this is the tree. So here, what are the possible traversals we can make, right? There are two kinds of traversals. One is the depth-based traversals. We can call depth-first search. You can say depth-based traversals, and then other one is the breadth-based traversals. Depth means I keep on going down and then search. Breadth means I go by levels. First I go with the 0th level, first level, second level, or it could be reverse level. Go to the last level and then come down to the 0th level, something like that. So each kind of traversals, based on the problem. If you look at any kinds of problem, if somebody wants to, somebody asks you to search some element or some problems, maybe we'll discuss the different set of problems, and also we'll come to know for what kind of problems we should use what kind of traversals to figure out the solution. So here, what are all the different depth-based traversals, right? There are three kinds of depth-based traversals. One is the pre-order traversal, in-order traversal, and then post-order traversal. These are all the depth-based traversals. So what do you mean by pre-order traversals? The pre-order traversal is first visit the root node.
Yogesh, one question. Could you please repeat what the core difference between depth and breadth is?
Yeah, it is simple. See, the depth-based traversal is I'll go down. See, if I want to search 400, right? Yeah. I go to the 200 and then I go to the down.
Okay.
I am going towards depth, down.
Okay.
But if it is a breadth, what I do, I'll search 100 first because it is at the 0th level, and I search all the elements in the second level. I search 200 and 300. I will not touch any of the child nodes until I finish all the current nodes which are part of the current level.
Oh, okay, okay.
Assume
So
I have a 6
breadth is level based, is it?
yes, exactly, level based.
Okay. And depth is like you go from the root towards the leaf, kind of.
Exactly. No, exactly.
Okay. Directly you go to the leaf, is it? Without
Yeah.
traversing the.
Yeah, I go say there are various ways. Like the intent here is to go to the child only, not to the its cousin nodes. Like for
Okay.
200, 300 is is sibling node, right? Not to
Yeah,
that.
yeah. Correct.
What I need to do is I need to go its own children node. It could be left or right.
Okay.
The
Oh,
left
once you cover that, you come back and backtrack and come back to the sibling node. Is it something like that?
exactly. Yeah.
Okay, 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 okay. Understood. Okay.
Yeah, that's correct. So these are all the possible, depth-based traversals. The one is a pre-order, and the next one is in-order, and the third one is post-order. What is a pre-order? If the tree is 100, this tree, right? So visit root first. That means 100, and then visit is left part of the subtree, and then visit right part of the subtree. This is the pre-order traversals. That means I visited root, that means 100, I went to the 100, and then I need to search the left part of subtree. After that, then go to the right part of subtree. So again, when I come at the left part of the subtree, this guy, I need to parse this guy, right? So print the visit the root, that means root is 200. I print root, and then complete the left part of the subtree. And then I come here, the print what this is guy is my root, a print root which is 400, and then visit the left part of the subtree. The left part of the subtree is null, and then right part of the subtree is null. So I visited, I am done with 400, and I'm done with 100, I'm done with 200, I'm done with 400. So once I'm done with 400, go back to its parent, which is 200, and then I need to parse the right part of the subtree, right? Go with the right part of the subtree, which is 500. Then I'm done with 500, 400, 200, 100, right? So then the outer part of the complete left part of the subtree is done with respect to 100. I need to search with the right part of the subtree. So here print 300, then left part of the subtree first, then 600, then right part of the subtree which is 700. If you look at it, this is the flow is 100 to 200, 200 to 400, and then 500, and then 300, 600, 700. I am searching the current element, I mean processing the current element, and then its left part of the subtree, and then its right part of the subtree. It's a bit confusing. Okay, maybe I will see, I'll take 10, 20, 30. Pre-order traversal is first visit root, that means 10, and then 20, left part of the subtree, which is 20, and then right part of the subtree, which is 30, right? But what if I have 40 and 50 here? For this example, first I need to do visit root first, 10 correct, and then visit left part of the subtree. You can take the left part of the subtree. That means 10, left part of 10, and then right part of 10. Okay, what is the left part of 10? If you look at it, 20, 40, and then 50, right? So what is the formula here? First root, and then left subtree, and then right subtree. So what is root here? 200. Print 200. Okay. And then after printing 200, for this particular value, I'm defining. After printing 200, the left part of the 20 and then right part of the 20. Correct, right? So left part of 20 is 40, right? So that means I can substitute L of 20 is equal to 40 because it doesn't have any, 40 is the leaf node. Again, 50 is also the root node, right? This is the right part of subtree. That means 50. So answer for L of 10 is 20, 40, 50. Correct, right? So what is the answer for right of 10? So assume I'll insert maybe 80 here once again. So R of 30 is I need to, I figured out answer for 10 and I figured left of 10 is also done. I recursively did it. And what is the right part of the subtree? Right, for R of 10 is I need to figure out the answer for this particular value, right? So what is the formula? Root, left subtree and right subtree. So I need to find out for R of 10, right? What is the root? Root is 30 and then L of 30 and then R of 30. R of 30 is null. It doesn't have any right child. So we can ignore this. What is L of 30? Only 80 is there. I can substitute 80 for this one. So what is the answer for R of 10? The 30 and 80. So for this if you look at this level, answer is 10 and L of 10, what is the answer? 20, 40, 50, 20, 40, 50. And what is the answer for R of 10? R of 10 is 30 and 80. So this is something like 10, 20, 40, 50, 30, 80. This is one of the depth-based traversal, which is pre-order traversal, wherein we have to visit the root node first, then process the left part of the subtree, and once the processing of the left part of the subtree is done, process the right part of the subtree. Is it clear?
Yes, Yogesh.
Fine. Okay. Now, okay. Again, if you look at it, few weeks ago we had discussed about stack, right? In stack also, we discussed about stack, and then after that we had discussed about queue. See, both stack and queues are used as auxiliary data structures in case of a while solving the tree problems. See, if you look at it, I go in the depth based, right? So in depth based, I definitely I can use stacks to store the each levels of data. But if I want to do a level based traversals, say 100, 200, 300, this is my level based, right? See, I can store 100 queue. I can store all the levels of, all the nodes present in the given level in the queue. If my requirement is to do the level based search. Yeah, we'll come to this point just after some time. So now let's focus only on the depth based traversals. 10, 20, 30, right? See, the pre-order traversal was visit root first and then visit left part of the child and then visit right subtree. So what is in-order traversal? So in-order traversal is a little different. That means visit left subtree first and then visit root and then visit right subtree. So what does it mean? That means before processing the root node, I need to process the left subtree first. See, this is my left part of the subtree, right? So 20. And then once the left part of the processing of the left subtree is done, process my root, which is 10. And then after that process the right part of the subtree, which is 30. See, since it is only one node, I'm directly writing this. If it has multiple nodes, obviously it definitely changes. So let's take 8, 6, 7, and then 9 for this one, right? So what is how do I do? That means I need to process the left subtree first, right? This is my left subtree. So before processing 10, I need to process this particular thing, 20, 8, and 6. So what is the answer for this? So here also I need to process the left subtree first and then root and then right subtree. With respect to this subtree, the answer is something like 8, 20, 6, right? Left subtree first, root next, and then 6. This is for this left subtree. And then what is the root of this? Root of this is 10, that is correct. And what is the right subtree? Right subtree is, if you look at it, 10, 7, and then 9, right? Again, left subtree needs to be processed first, and then root, and then right subtree, right? So that means 7, 39. For this diagram, the answer is 7, 39. That means for this thing, this left subtree, answer is 8, 26, and then the root is 10. I'll write 10 as it is. And then The answer for right subtree is 379, right? For the 379 answer is 739. This is called, this is the in order traversal. Is it clear?
Yogesh, in that case, we'll have this different modes of traversal, right?
Yeah,
So,
yeah.
let's say when we search for a particular element, let's say, then the search will be faster in cases of some kind of traversals, right? In that case, as in,
Yeah, so if you look at it, search pre-order traversal I can do. The as and when I just while processing the route only I can decide. I don't have to go to the either left sub part of the subtree or right part of the subtree.
okay, okay. So pre-order will be kind of faster for search operations, is it? In that,
Yeah, because we process route first before processing left or right subtree. So I can get the answer very quickly. Correct, right?
okay, yeah, yeah, true. But
Yeah.
then in that case, when are these traversals used in that case?
Yeah, that is what. I'll come up with different set of problems for
Okay,
what
okay,
kind of traversals I should use to solve certain problem. It's
okay,
again based on the problem
okay, okay,
statement.
okay, fine.
Yeah, I have picked couple of problems so that to cover both kind of traversals. When should I? First question is whether I should level based or uh,
Depth
depth
based.
based. Yeah, in case of depth based, whether I should use tree order traversal, pre order, in order, or post order. I have some examples. So
Okay,
maybe once we cover those basic set of examples, you will have some idea.
okay, okay, okay.
Okay. Say for example, yeah, I need to check. It's again based on the problem. Before processing my route, whether I should complete my left. Yeah, maybe once we go through the problems, we will understand better. This is clear, right? The in order traversal.
Yes, okay.
Yeah. So then is a post order traversal. See, post order traversal is same thing. I assume I have 10, 20, 30, 40, 50, 60, and then 70. The post order traversal is, see, I left process the left subtree first, process the right subtree next, and then process the root. Left, right, root. So So with respect to this example, this is the left subtree, right? I need to process the left subtree first. What is the left subtree? Left subtree is 20, 40, and then 50. And what is the root? Root is 10. And sorry, root is again, so this is the right subtree, not root. What is the right subtree? Right subtree is 30, 60, and then 70. Then what is the root? Root is 10. So I need to first complete the processing of left subtree, processing of the right subtree, and then process root. So how do I do this? For this left subtree, the answer is 20, 40, 50. The tree is 20, 40, 50, right? Here also, I need to process the left subtree first, right subtree next, and then root. So here, what is the left subtree is 40. What is the right subtree, which is 50, and what is the root, which is 20. That means left part is done. What is the right subtree? It has a 30, 60, and 70, right? Here also I need to apply the same rule, like process the left subtree first, process the right subtree next, and then process the root. So here also it will be something like 60, 70, and then 30. This is the left, this is right, and this is. And then what is the root? 10, right? So if I substitute this in case of LS, and then I substitute this in for RS, and then root is 10. The answer is 40, 50, 20, 60, 70, 30, and 10. This is the post-order traversal for this particular tree. That means I need to process left 40, 50, 20, then 60, 70, 30, and then root. This is the post-order traversal.
Yogesh, one small question.
Yeah,
Uh, so in that case, this naming that in order, pre and post, is it with respect to the positioning of the root? Is it in the order that we have?
yeah, yes, yes.
Oh, okay. So in order means like root is in between left and right.
Yes, that's
Okay.
correct. Yeah. So that is why we process left subtree first. Then since root is at middle, then root and then right subtree.
And for post, it is like root is at the end, and
Yeah.
for pre, it is like root is at the
The
beginning.
beginning. Yes.
Okay, understood.
It's
Okay,
based on the positioning of the root. That's
okay,
correct.
okay, okay.
So is this fine? Depth-based traversals theory part. Shall we try implementing this? If theory is clear, we can jump into the implementation. I'll tell the algorithm how we can go ahead, right? Or is it not clear for anybody? Okay, so let's take the first traversal, which is the pre-order traversals. Just I'll take the same example 10, 20, 30, 40, 50, 60, and then 70. So we know, right, that what should be the output. Output I should process in case of pre-order. The root I should process the root first, correct, right? So once I process the root, I need to process the left subtree. That means here I come here, and then for this guy also first process the root and then go to the left subtree. And then if I have maybe 90, and then I go to the left and process it. First, if you look at it, I'll process 10, 20, 40, 90, and then I go to the right part of the subtree, right? So while this is at root, I mean I'll take the current also to the root. Maybe you can just it's a variable pointing to the root. First, print the whatever the value current is pointing to 10, right? So I'll print 10 first. Then what should I do? I should go to the left. I should process the left subtree, right? Move the current to the left hand side. The current comes here. So then process this guy 20. And that means I print it. And then go currents towards left. Then print it, which is 40. And then go towards left, come. Then which is 90. Then go towards right, which is null. So that means if it is null, I should stop it, right? So once current goes to the null, somehow I need to go back to the 90 and check whether I have any right subtree. Do I need to process that? So and then if there are, assume I have one more 100 and 200. This is a bit complicated, right? So that means if I look first, try to answer should be 10, 20, 40, 90, then 100, 200, 50, 30, 60, and 70. Correct, right? So that means while printing it, I need to go back to the last node which was processed and then check whether it has the right nodes or whether nodes towards it right or not. If there are any, again you process it. Assume here also I have 100, 200 and 300, right? So once I process 10, process 20, 40, 90. But after that, I went towards the left part, but it is null. That means all the processing of the left subtree is done with respect to 90. Then go back, figure out what was the node I processed last time. That means 90. And after going back to the 90, check whether does it have any right nodes or not. If it has a right nodes, then we need to process that. That means just I need to keep track of all these elements, and I need to go to the element which was processed last. That means this is in the last in first out order, right? I need to have some data structure which should give the ordering like last in first out. That means I process 90 last, and then I need to process the right nodes of the element which processed last. So 90 I processed. After that, go to the 90 and then go to the right of 90, 100. So current comes here. Again, check current is process current, which is 100, and then go back towards left, then process it, which is 200, and then go back to the left, which is null. Then go back to the 200, and then it doesn't have any right, leave it. Go back to the 100, it doesn't have any right, leave it. And then go back to 40, it doesn't have any right, leave it. Go back to 20, and then make current to point here to the 50. Then print 50. Then after that, 50 is also done, 20 is also just now done. Then 10 of right, current pointing to 30. So process 30, then current comes left, which is 60. Then go back to the 30 of right, the current comes here, then print 70. Are you guys finding difficult, or it's fine?
So it starts from left side and it goes to the bottommost left node, is it?
Yeah, because here the formula here is I need to process root first. That
Yeah.
means whatever the current is pointing, that is the root, right? I
Yeah.
process that. Then I need to go to the left subtree.
Okay.
Go to the left, process it. Go to the left, process it. Go to the left, process it.
Okay. Till the point where left gets exhausted, we have to keep on coming.
Once here, after this current gets exhausted, right? Then
Yeah.
I need to go to the 90 of right. Right
Okay.
of 90.
Okay. Because that is the only path from that node. So we have to traverse that path. Okay.
Yeah, that is correct. Say here I have 200. Before processing 200, I need to process the right subtree of, with respect to 90, right? With respect
Correct.
to this subtree, I need to process root, I need to process left subtree, I need to process right subtree.
Okay.
That
Okay.
is how it is, right?
Yeah. Correct.
So I
at
need
every level, it is considered as a subtree kind of,
yeah,
which we have to kind of parse.
exactly.
Okay.
So after completing this particular subtree, go back one level, complete this particular subtree, go back one level, complete this part of the subtree. If from this entire right subtree is done with respect to this particular root, then
Okay.
try with the right subtree. Again, it's we need to, at each level, I need to figure out the answer with respect to that particular subtree.
Okay, understood. Okay.
So that is the bit tricky part here. Once you get that, the remaining part is, simple. 50, 60, maybe I'll call it as 70, 80, 90, 800. Okay. Correct, right? With respect to this subtree, this is the left part of the subtree. And again, with respect to this node, this is the left subtree. And this is the right subtree. And with respect to this node, this is the left subtree and this is the right subtree. So again, while solving the problem, we have to figure out the answer for each particular subtree. So here, if you look at this 10, 20, 30, 40, and 50, right? So I need to process 10. That means current is pointing at 10, assume. I process 10. What do you mean by processing? Just I'm printing here, not doing anything, right? So I'll print 10 here. Then I need to process the left subtree. So in order to process the left subtree, what should I do? I do current is equal to current of left. I comes here, right? When current comes this point, again, I need to process root. That means print, I printed 20. Again, once the processing is done, go to the left part of it and I need to do left subtree and then right subtree, right? So do current is equal to current of left. Current comes here. So process it. That means 40. So then do current is equal to current of left. That means current is null. That is done. So once this part is done, I need to assume I have 8 here. I need to process this 8 first. So that means go back to this particular node. Somehow the current is back to this particular node and do current is equal to current of right. Somehow we have to make current to point to 8. So that how can I do? If you look at it, I processed 10. then I process 20, I process 30, and my intention is 10, 20, 40, and I need to go back to 8, right? I need to somehow point to right. See, if you store the pointers like in the stack based, like I sources 10, put into the stack, 20, put into the stack, 40, you put into the stack. Once stacks get in the left subtree gets exhausted, get the top element from the stack, that means 40, and go move current is equal to 40 of right. So current comes here. Then you process it. Then processing of 8 means I just printed 8 and then go to the left part of the subtree, which is null, no point in going, and then right also no point in going. So then once that is done, you pop this particular element 40. This is done, right? So again you do get the top element from the stack, which is 20, and make 20 current to point 20 of right, which is 50. While doing this one, I can pop 20, correct, right? So again, if there are any 5, 50, 60, 70 here, keep moving them 50, 60, 70, whatever the elements into the stack while processing it. So 50 is also done here. Then get the top element from 10 and then make current to point 10 of right. So current points here and then pop this guy. So process 30. That's all. It's clear, right?
Yogesh, one small
Yeah.
question. Is
Yeah.
it somewhat related to that divide and conquer strategy in some way, where we kind of break down the problem into smaller subproblem and then solve it and then merge the result at the end or something? I mean,
Uh, yeah, actually, somewhat related, but the divide part is correct. We are dividing into each subtree and finding a solution, but we are not merging anywhere here.
but the final result we are somehow concatenating and showing, no? Like when we display the final result left, let's say root left, right? Um,
Yeah,
so while displaying, it's not like merging, is it?
I'm just as and when I figure out the answer, I am in one way we are dividing the problem and then figuring out the answer.
Okay.
But conquer part, um, but it is because in tree itself we go either left or right, somewhat related, but in conquer part I'm thinking whether it perfectly suits there or not, because 70% it's correct, because first we are dividing the problem and
Okay.
figuring out the answer for that smaller problem, right?
Yeah, yeah.
But in that, if that is the case, I need to divide this, divide this, divide this. I need to get this smaller answer first. But
Okay.
in case of in-order traversal, that is kind of applicable. But here, I'm dividing here only, but I already processed them, right? I got the answer here only.
Okay.
It's
Okay.
somewhat
So,
related, but not
okay.
exactly.
Okay. Okay. So you're here. We are not processing or something. We are just displaying it. So that is
Yeah.
why maybe conquer might not fit, right?
Yes, yes.
Okay. Okay.
Okay. So if we understand pre-order, right, then in-order is little, I mean, it's something similar to pre-order only. Let's quickly write the pseudo code 10, 30, 20, 30, 40, 50, right? So, and then I'll take 100, 200 to cover all possible cases. See here, if you look at it 10, 20, 40, I need to process first, and then 100, 20, 100 and 200 I need to process, then 50 I need to process, and then 30 I need to process. See, after that also you take 100 here, and then after processing 10, 100 and 30 I need to process, right? So current is at here. So I'll say while current not equal to null, this guy is not equal to null. I'll process it. Process means I'll print it. 10 is print, and then after processing 10, push 10 to the stack. I push 10 to the stack. So then go towards left. Current comes here. So then check whether it is null or not. 20 is not null. That means process it. Processing means here I'm printing it 20, and then push the same current node to the stack. Basically, this is I'm not pushing the value here. Here it's the address of 20. It is the address I'm pushing. So again, I do current is equal to current of left. Current comes here. So current is 40. That means it is the address. This object is not null. So print the value of that particular current. So which is 40, and then push 40 back to the stack. So my stack currently contains 10, 20, and then 30. Then you do current is equal to current of left. So current comes somewhere here. That means it's exhausted. Current is pointing to null. So now that means left subtree with respect to 40 is done, right? I need to process the right part of this particular subtree. The last, just whatever the element we processed, the last element, which is 40. So I need to get the I40 back, right? How do I get it? Because since I'm storing into the stack, the whatever the last processed element, I'll get first. So I get that particular element. So do after getting that current, just do current is equal to current of right. So current comes here. So how do I do that? Current is equal to get top element. So get the top I do. So that current points to this particular thing. Then you do current is equal to current of right. So current comes here. So that means I stored 40. The purpose of storing 40 into the stack is I want somehow I need to go to the right of the 40. That is why I was storing in the stack. So the purpose is done, right? So pop it. So again, current is 100. So process 100, that means which is print 100. Then after that, you put current back into the stack. That means 100 I put into the stack. Then do current is equal to current of left. Current comes here. So print process 200, the current which is 200, and then put current is into the stack which is 200. So then current is equal to current of left. Current gets exhausted towards left. So execute this one. That means get the top element of the stack which is 200. So current comes here. So current comes here, and then do current is equal to current of right. That means right also it exhausted. So before going right, I need to pop right. I'll pop it. So then when current exhausted, even both whether it in the left hand side or right hand side, then pick the next element which is present in the stack. What is the next element which is present in the stack? 100. So do current is equal to get top, which is current is pointing to 100. Then pop it. Then do current is equal to current of right. So again, which is null. So that means it is exhausted. Then do current is equal to current get top of the stack, which is 20. So that means current is at here, right? So do current is equal to current of right. Current comes at this point, and then pop this from stack. So then process 50. That means I printed 50, and then I put 50 back to the stack. So then do current is equal to current of null, left. That means which is null. So get the top element from the stack, which is 50. Current is pointing at here, and then pop it, and do current is equal to current of right. Current comes here again, which is null. So then that means then get the top element from the stack, which is 10. So that means current points at this particular point, and then pop this particular element. Do current is equal to current of right. Current comes here. Then you process current, which is 30. That means I'm printing it, and push 30 to the stack. Then do current is equal to current of left, that is 100. Then while current is pointing at 100, process 100, that means print 100, and then push 100 to the stack, comes to the 100, and then do current is equal to current of left. So current comes here. So that means it's exhausted. Get the top element from 100, and then that means current comes here. Pop it. Do current is equal to current of next. So that is null. There is a no up. That means I can't do anything because that right is null. I can't process the null. So again, get the top element from 30, which is here. So current is equal to get top, which is comes to the 30. Then pop. Do current is equal to current of right. So current is here. So when my current is null and my stack is empty, that means my processing is completely done. So this I was printed. Whether you print it, whether you store it to some other data structure, or whether you put it in a list and return, it based on the just somehow we are storing all the elements in a pre-ordered way. Is it fine? Is it clear?
Yes, Yogesh.
Okay. Fine, then let's quickly implement this. We want I'll remove this. Okay, let this. Fine. See here, if you the answer, the input is given as 1 null 2 3, right? The representation is there. The input is in terms of level based. One is at first level, the null is at the second level. That means this part, it is something like 1 null 2 3, right? It is something like this. This is like 1 1 null 1 null 2 3 null. This is 2. Again, since it is null, I can't go there. 3. This tree is something like this. Yeah, 1 null 2 3. Here only they're explaining, right? 1 null 2 3. So if you look at the pre-order traversal for this particular thing,
Yogesh, one question.
yeah,
Then after 3 also they should have given null, no? In that case, as in
yeah,
at level.
they would have given, no, that means after 3, there is no point in giving null. If they want to insert it at year, like year 20, that time they would have given 3 null and 20.
Okay, 3 null.
Correct, right? See, that means if you look at it, 1 null, 2, 3 null, then 20. This is something like null. This is for processing. Okay, or else what I can do is, let's see here. Can we, this is 3. If I give null and then 2, how do I visualize? Tree visualizer, I'll apply here. See,
Okay.
1, 2, 3, null. 1, 2, 3, null 2. That means if I want to insert at the right, okay. If I give something like this, it is only 1. Okay.
Okay.
And if I give 2, it is inserted at left.
Okay.
And if I give 3, it inserted at right. But
Okay.
I want to insert, if I give this, it is, that means I want to insert only at right, and I want to insert null at left, right? That is, if I do this, it is something like this.
Okay.
Okay.
So it means that
And then after 3,
after last leaf null is not required, something like that. Is it?
yeah. See here, you are saying after 3, whether you input null or don't put null, it doesn't make any difference.
Oh, okay.
Correct, right? But
Okay.
assume I want to insert something at right hand side. So then I need to put null here so that the left child of 3 is null, and then insert something 34. It inserted 34 towards right.
Okay. Okay.
But if you don't put null now,
Huh.
it insert 34 at the left hand side.
Okay. Understood. Okay.
Yeah, I think since the tree visualizer, right, we can check through that. If
Okay.
I put null here, then go, it happened 1 null 3, 1 null 3, and then I want to insert 34 at the right hand side, put 34. So it came at 34, right?
Yeah. Yeah.
So if you put instead of null, if you put 23, 23 comes at left hand side.
Okay. So
Since
only if some insertion is required.
pattern,
Okay.
yeah. This is just to read because in the lead code they are reading input based on levels.
Okay.
Just
Okay.
to keep it simple.
Okay.
So, visualizer is fine. So now, right, we want stack as an auxiliary data structure here, right? So what I'm thinking is let's since we already implemented stack, we can go to our stack folder and then I'll just pick stack. Correct, right? Let's not implement again. I'll take this stack and then create. This is I have stack. So I'll create my stack is equal to stack. Okay, I created my stack. So then what I need to do, I'll take current, I want to, I'll not disturb root, I'll just take my current is equal to root. Sorry. Okay, current is equal to root. See, if you look at this thing here, what we did, current is pointing at here. If current is not equal to null, do current, process it, and then do current is equal to current of left. Correct, right? So while current not equal to none, process current. That means what do you mean? What do we mean by processing here? Just they expect answer to put it in a list and return, right? So I'll take my result. I'll take result is equal to array. Then what I'll do is current result dot append of current of val. Look at this is the value and this is the left child and this is the right child. That is how is the syntax, right? So I'll put current is not equal to none. Just I am appending the current dot value. That means this is the processing part. And after that you do current is equal to current of left. So with this particular, I'll take 10, 20. So I visited 1 in this while loop. Is not equal to none. So append result dot append is equal to current dot value. We put 1 to this one and do current is equal to current of left. Current of left comes here. So this is not null. But then you print this value to the list and then do current is equal to current of left. Current comes at here 23. Then 23, this is also not null. So put it into the list and then do current is equal to current of left. So current gets exhausted. So meanwhile, as and when we push, we need to push the current into the stack, right? So I need to do my stack dot push of current. So with this example, I have 1, 20, 23 in my stack. So I need to take out the last element from stack and then process the right element. Just make current is equal to current of right. And then you just repeat the process. So this is done. Once current is none, get the top element. That means current is equal to, how do I get my stack dot top? This is my top element, and then you pop it. My stack dot pop. I popped it. So do current is equal to current of right. So once it goes current is equal to current of right, again it comes back to the same while loop and keep doing it, right? Correct, no? That means
Yes.
I had I had 10, I had 20, I had 30, 40, 50, and then 60. Current was at here. I did 10, 20, 30. 10, 20, 30, and then current is equal to current of left. Current is exhausted. So this part is gone. Then I need to get to the top of the element by doing my stack dot top. So my stack dot top is 30. So I do current is pointing back to 30, and then I'm doing current is equal to current of right, and then pop. I popped it. Current is equal to current of right. So current is again null. So in that case, what should I do? Again, I should go back to the while loop here. It comes here, but it is null. Again, get the top element, which is the top element 20. Current is equal to top. Then do my stack dot of pop, and then current is equal to current of right. So I did pop and do current is equal to current of right. So when current is at this point, I need to go back to this while loop and then keep executing it. Current is not none, so process it. That means I add that 40 to the result array and also 40 to the stack. Then do current is equal to current of left. Current comes here. Then you print or add into the list and add it to the stack. Then current is equal to current of left. So when it is exhausted, again you come to this point. So current is null. So then make current to point to the last element of the stack, and then pop it and go back to the right. So here that means what I need to do is this I need to do, keep executing it, right? While true, this is this, this is this. So after when it comes at this point, if my stack is empty, just you come out. If my stack is empty, is there, is empty, is there, is empty, equal to true, just return result. That's all. Just run it. See, if you look at it, the input is 120, 30, 20, 34. Then the output is 120, 23, 34, 3, and the expected is also same. Let's test with 203, 3, and then I'll make it null. If you look at this, this is the tree, right? The answer should be 1, 200, 34, 3. 1, 200, 34, 3. Then maybe 34, I'll add 20, 34, 20, 33, 40, 40 is added at this point. Okay, then I add 111, then 200. Can you tell what should be the answer for this particular subtree? Can somebody tell? Sripat, can you give it right?
So it is 1, 234, right?
Yeah, yeah.
Then you do the, that goes into stack, and then you have one more, 11.
Yeah, 1,
That goes in
234,
between.
11. Yeah. Then
Then you start with right? So then you have 200,
yeah,
and then you have 3, 2, and 340.
320, 340. Yeah. That means
Okay.
answer should be, I'll just write down whatever you are told. 1, 200, 34, 11, 200, 3, 20, 340. Correct, right? So I'll just cut it. Then I'll run the code. See, okay, where should I'll paste it here. This is what you are told, right? 1, 234, 1 output 1, 234, and then 11, 203, then 11, 203, 20, 340, 20, 340. The expected is also same.
Right.
Yeah, let's I'll switch this off and then I'll submit this. Yeah, this and already. Okay, if you look at the details, see it executed 68 test cases. All of them are passed. So, any doubt?
No issues.
Okay, I'll tell one more way to do this. That is the simple, super simple way. See, I have 100, I have 200, 300, 400, 500, right? So just check if my root equal to null or none. I don't have to do anything, right? So just I'm returning. This is my terminating condition. Okay. Else, what I do, I need to process this guy. So 100 process, that means add 100 to list, our result list. Processing is done. See, this is my pre-order. I'll pass root. This is my function. Okay. This is done, right? So I did pre-order of 100. Processing is okay. This. Then once that is done, I need to figure out the answer for the left subtree. I'll call the same function pre-order of root of left. Okay. So this is my function stack pre-order of 100. Then I call pre-order of root of left, which is 200, right? So the stack is something like this: pre-100 of 200. The function stack I'm talking about. So whether this guy is null, no, this is not null. Then what it does, I add 100 to the list. That means in this particular stack, I added 100 to the output array. Now here I added one more. I'll write the result here: 100, 200 to the output array. Okay. Then I call pre of root of left. What is the root of left? This is pre of 400. I call. So again, this is not null. Add 400 to the list result. This is add value to the list 400. Then you call pre-order of root of left. So root of left I call. Root of left is pre of null. Left is null, right? So what is this? If root of equal to null, I'm returning this. This function returns, so it comes at here. So at this point, if I have any elements, I need to process those elements, right? Right hand side. Left processing is done. Now you do pre of root of right. So I do pre of root of right, which is null. Again, I call the function with pre of null. So again, it goes to this particular function, and since it is null, it returns. So this from 400 for this thing, left is also done. done, right is also done. It returns from this function call. So pre-as that this part is done because 200 left is done, right? So now I need to process at right hand side. So here call stack goes from pre of 500. So again pre of it goes to the pre of left, which is null. So it returns. Here I print 500. Again I need to call root of right. Root of right of 500 is null. Again that is also written from here. So when I process the left of this and right of this, I need to return this, right? I come back to this 200. Then for 200, I processing the left part is done, processing the right part is done. So return from the function stack. So now my current is at here. So then I do, since I'm doing pre-order of root of right, current I call pre-order of 300. So again it pushes, while processing 300, you print 300 here, 300 here, so here 300 here. Then you do pre of 300 of left, which is null. So that particular thing is null, so it comes back. And then you do root of right, right? Root of 300 is again null, pre of null. Again it goes to the function, if it is null, it returns. Then I processed left part, I processed right part. That means 300 is done. So you return from 300. So this is also after that I popped, right? So once that is done, then return, that's all. Yeah, 100 for 100, left is also done, 300 is right is done. So left is also done, right is also done. I need to pop 100 from the call stack. So this is the something similar what we had implemented here, but here we had created our own stack and we did push pop accordingly with respect to the logic. But here, if you look at the problem carefully, by leveraging the recursion, calling the same function again and again, I can easily solve the problem. So these are all the 3-4 lines of statement I need to make in order to solve the problem. Let's go back to the problem here. I'll go to the problem description. I implemented this, right? Reorder traversal. So here, instead of order traversal, I'll comment out this part. Okay. I'll comment out this part. I'll write it in a recursive way. If root equal to none, return. So I don't do anything. Else, I need to process the current root part, right? So I'll take self dot result. This equal to self dot result. I will in the initialization I'll do one more thing. Self dot result or else sorry okay, I'll take something. This tree node part where I should take okay, I'll take some area. Okay, I'll take some out variable, declare outside variable only here only. Self dot result is equal to this one. Or I can take only result. Self result dot append of root dot val. It is not null, right? Then I'll do pre-order traversal of root dot left. Then pre-order traversal of root dot right. Just run this. t self dot okay, I'll do one thing. Self dot result run. Okay. This is not defined.
Yogesh, I guess it has to be put in a constructor, right? The
Yeah, this one. Okay, I'll put it here. Self dot result is equal to this. Here I do self dot not no, this is
I think we have to instantiate that class inside that function before we use, because result
they
is
are
part of
actually
that.
they are
Uh,
doing somehow based on this input, right? They're instantiating this particular node class and linking it. They're passing only root node. So I don't think we can create one more our own variable here. What else I can do? Something I forgot. Okay, I'll do one thing here. Just for the purpose, I'll do print just to evaluate the result. I'll just print the root dot var. See, if you look at it, the answer 1, 234, 11, 200, 320, 340. Order is same. But here we need to put this into a list, right?
yeah,
So, so, so then dot result.
we can write an init function for the solution class, and then inside that init we can maybe define the result variable.
Cell something like this, right?
Yeah, yeah,
Cell dot
yeah, yeah.
L. Yeah. But since if they have any their own custom constructor, it might go
Yeah,
for a task.
we
Let's
can
see.
try this. Yeah.
Self dot result dot append dot current dot val. Current is not current. It's root. Sorry. Root. Self dot result dot append
I
to
think we
dot.
have to return that result, no? If root is equal to none.
Okay. Got it. Now I got it.
Yeah.
Yeah. This one I'll write some auxiliary function here. Def preorder util, then self, then root. Then I call if I'll move all this function to this. Okay, then this preorder util. Here also pre-order util. So once I'll call pre-order util of root. Correct, right? So then I'll do return self dot result. So Since we have this is applicable here also, right? This should be fine, no?
Yeah.
Let's run this. Pre-order utility is not defined. This should be self dot pre-order. Oh, double L. Yeah, 1 234 11 220. I'll just remove this. Then I can submit. Yeah, same. The both the other one also took 20 milliseconds. This one also took 20 milliseconds. See, the only problem with recursion, right? It's easy to write, but we need to visualize it properly. The how the function gets called, how it puts into the how the all the stack frames are returns and gets added. And again, if something goes wrong, the recursion is bit hard to debug. But while writing recursive programs, we should be very careful. And while writing recursive programs, we should not forget to put the terminating conditions. If you don't put terminating conditions, it goes in an infinite loop. These are all the basic things we should keep in mind while writing any of the recursive programs. So, is it clear? The pre-order part, at least.
Yes, Yogesh.
Yeah.
Yeah. Yes.
Yeah, fine. We'll do one thing. We'll take a break and then we'll come back and discuss other traversal methods. Is that fine?
Yes, Yogesh.
Yeah. We'll yeah, 10, 6. Okay, we'll come back after 10 minutes.
Okay.
Yeah. Okay. Mm, Hi, Sripati. Hi, Naveen.
Hi, Yogesh.
Yeah. Okay. Will any doubts in the previous class pre-order traversal? Okay, then we'll jump to the next one and probably we'll try to solve the problem together. This one. Uh, the problem here is in order traversal, right? It is it. Fine. See, let's have 10, 20, 30, 40, 50. The pre-order traversal was 10, 20, 40, 50, and 30, right? What is the in-order traversal? In-order traversal formula is something like visit left subtree first, then visit root, and then visit right subtree. Correct, right? So what is the left subtree here? This is the left subtree. So that means 20, 40, 50. I need to process first 20, 40, 50. Here also I need to apply the same formula recursively. Left subtree, roots, right subtree. Here the left subtree is 40, root is 20, 50 is the right subtree. So ultimately the answer for this is 40, 20, 50. And what is the root here? Root for this level, the root is 10 only. And what is the right subtree? Which is 30. So since it has, okay, I'll add 400 and 500. So what is the right subtree for this particular level? 30, 400 and then 500. So here also I need to apply this formula recursively. Left subtree, root, right subtree. This is the left subtree, this is the root, and this is the right subtree. So the answer would be left subtree, root, and then right subtree. So the overall answer is 40, 20, 50, 40, 20, 50, and then 10, and then 400, 30, 500, 400, 30, 500. So this is the in order traversal. So any idea how we can programmatically solve this problem?
Uh, I guess we can just shift the positions of those things, right? In the previous code that you had, like
Uh,
the way we traverse left and right in that recursive code.
okay.
Uh,
Yeah, recursive. Yes, it's fairly simple. Just we need to. Uh,
we have to shift this, right, in
yeah,
middle.
just I need to put this and then put it in the middle.
Yeah, yeah.
Okay, that is a fairly simple solution. But if you look at this problem, that is, yeah, recursive solution is trivial. Could you try it iteratively? If you do it iteratively, right, maybe, yeah, we can do both. It's a recursive solution. Whatever you are told is perfect. Just I need to shift this particular value in between
In
root
between.
or
Yeah.
left and root or right. That's all.
Okay.
But how does it work? I mean, maybe we'll give a try with the iterative one, and also we'll give a try. We'll modify the recursive one also.
Okay.
So, can you guys think how we can solve this problem iteratively? See, again, if you look at this, was the iterative solution, right? This was the same thing. I need to have a stack here, and then maybe I need to have a while loop, couple of the same part of the thing. Maybe I'll explain theory, then we can come back and then see how we can modify the existing code, right? So this is my root pointer. This is my root pointer, right? And then I take current equal to root. Current is also pointing to the root of the node. See here, I need to print the left subtree first. That means leftmost node I need to print first. Correct, right? So first my goal should be go to the leftmost node. That means what I'll do is while current not equal to null, keep going it. Current is equal to current dot left. Current comes here. So this is not null. So current comes here. This is not null. Current comes here. This is null. So while doing this, what I need to do, I keep track of all the nodes in a stack. So here push to a stack. So in that case, so I first root was pointing at this particular point that is not null. So I pushed into the stack, and then I moved current is equal to current of left. Current comes here. Again, the current is not null. So I push 20 to the stack, and then I do current is equal to current of left. So here current is not null. So again I do push current to the stack, which is 40, and do current is equal to current of null left. So current comes to the null. Correct, right? So now what I need to do, get the top element of, I need to point my current to this particular element and then process it. Because first part was to process the left subtree. So now I read the left subtree, then process it, then print the root or add the result to the list or whatever it is. So here if it is when current is equal to top of the stack, so current points at this particular thing, so then process it. That means add current to result array. So how do I get this? This make current is equal to top. Stack of top, it comes here, add current to the result, and then you do current is equal to current of right. So I go current is equal to current of right. Current comes here. So meanwhile, when I add result, that means my processing of this is completely done, right? Let's you do pop. I pop this. So 40 job is done. Then current is equal to current of right. That is also null. So this will not get executed. So this one I'm executing in an infinite loop. Okay, in a continuous loop. So again, 20 is there in the stack. Just get the 20. So while after getting the tab add to the result, initially I add 40 to the result. Then 20, I need to get the top of the stack, which is 20. and then you print 20 also. I printed 20. Then you make current is equal to current of rate. Current comes here. Current, right? So in that case, current is not equal to null. Add, I pop this also 50 to the stack. So then again, current comes to the null. Get the top element, pop it, add 50 to the stack. Then 10, pop this, print 10, then add 50 10th right, which is this one, right? Current. Current is pointing at here. Then current is not equal to null. So add to the stack. Then current comes, current is equal to current of left. Current comes here. 400 not equal to null. Then add 400 to the stack. Then current comes, current out of the, it gets exhausted here. Then go back to this point to this one and then process the right subtree. So I get the top. After getting the top, print that. That means I printed 400 and then I put the right and also pop this. Then 30 is there. Then again you get the top, print it, and then push current of right to stack. I mean, make current point to the current of right, 30 of right. So current points here. So I pop this. Again, it is not null. Current is not null. This push current is equal to stack. Push the value of current to the stack. Then again, current exhausted towards left. So current of, then get the top element which is 500. Then process it. Then put the current of right. Make current to point to current of right. So current is equal to null. So we already popped this, right? When stack is empty, when current is null, that means I processed all the elements. Just check whether it's in the right order or not. 40, 20. So 40, 20, 50. This is the left subtree for this particular node that is printed first. And then root. This is the root. And then the right subtree. This is the right subtree, right? Again, if you look at recursively, 400 is the left subtree. The 30 or 300 is the root. And then this is the right subtree. This is left subtree, this is root, and this is right subtree. Correct, right? Is it clear?
Yes, Yogesh.
Okay, let's try to code together. Maybe I'll. Can you guys tell? I'll just type because so that it will be clear for you also. If I keep coding, you might not get what's happening here. So just this is the code. So again, I'll take my stack implementation from here. Okay, so I'll take result is equal to array. Can you tell what should I write now? Or can you guys give it right? You can share the screen and probably you can try. I'll send the link. Can we do that? Or you want me to go ahead and implement?
I guess you can type it, Yogesh.
Oh, fine. Okay. Fine then. See here, if you look at this, um I'll do side by side white paper plus whiteboard plus this one. If you look at this 100, 200, 300, 400, maybe 500, then 800. See, first I need to process the complete left subtree, right? So I need to keep going here, okay, and
Yeah.
then keep putting them into the stack. So that means I should go 100, 200, 300, then 400. Once it exhausted, that means I need to process the last visited element, which is 400. That is the leftmost entry in the given tree, and I need to process that. So in order to get the leftmost element, I need to keep pushing all the elements to the stack. In order to do that, what I need to do is,
So first thing is while true you have to give, no?
yeah,
That
while true, yeah, that's something I need to do in an infinite loop. So
yeah.
this is the big outer while loop.
Yeah.
Inside that, what I
Current
need
not
to do is,
equal to null, right?
yeah, while exactly while current not equal to none. So push that I'll take a stack. It
Yeah.
says my stack is equal to stack. Okay. Stack dot push dot current. Correct, right?
Yeah.
Then
And
if
then
I do
current dot
that,
left.
yeah, perfect. Current is equal to current of none. So now it is I am at this particular point. So once the current goes to the null, when current points to the null, that means fetch the leftmost part.
Topmost.
Correct, right?
Yeah.
So fetch the leftmost part when
So
it comes to this
current equal
value.
to top, right? Here.
Yeah, current is equal to exactly my
Okay.
student on top. Then after that, I need to process that. That means I need to add that to the result.
Correct.
So result dot append, I'll do current dot value.
Okay.
Right? So once I added, that means this particular processing of 400 is done, right? So
Yeah.
there
Yeah.
is no point in keeping it in the stack.
Stack. Yeah.
So what I need to do is I'll pop that.
Yeah.
So current dot, sorry, my stack dot pop. So once after processing that, I need to go towards write and print, right? Process, right?
Yeah. Yeah.
So current is equal to current dot write.
Right. Yeah.
So when current points to the none, and then at this point, if stack is empty for whatever reason, that means
You have to
it
return.
is done, right? Yeah.
Yeah.
If my stack is empty equal to true, just return result.
We have to give and also, right, Yogesh? Oh, that is already there in the condition of the while, right?
This, yeah. Here it comes only if current is null.
Okay. Okay. Okay.
Correct, no? So we don't have to give that particular check.
Okay.
Run this code. Okay, the current is not, current is equal to root. I think 132. Let's write different. 2, 3, 4, 5, 6, 7, 8, 9. Can you guess the output for this one? This is actually right. Maybe I'll write 45 here. Yeah. What should be the output for this?
7,
Yeah.
3, 8.
7, 3, 8. Yeah.
Then 45,
45.
4, 9.
No, the before 4 is root, right? And 9 is left.
Yeah. 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 9, 4. Sorry.
9, 4.
Then 1.
Then 1,
Then 5, 2, and 6.
5, 2, and 6. Okay, I'll just cut it. And then I'll place it somewhere here. Then let's run this. 73845, 73845, and then 9415, 9415, and then 26,
Yeah.
and then 2. Correct, right?
Yeah. Yeah.
Perfect. So then I'll submit this. Yeah, it is same. It also took 20 milliseconds and then it would have executed around 60 odd test cases. Yeah, 68 test cases. So let's quickly solve this using recursion also. See recursion, I'll see this is what we had solved right in the previous one. Oh, we did not submit. Okay, we can write quickly, no problem. I'll write dev in order recursion recur util root self dot root if root equal to none return else in order recur util of root dot left, then I can add self dot result dot append of root dot val, then I will call this root of right. As Sripati suggested, I think just we need to change the position. That's all. Here. This is right. So here we had the init self, self dot result equal to empty. Here I can call here I can call this util. Correct, no?
Yeah. Yeah.
This util of root and then return self dot result.
Yeah.
And here this part of code will not execute. Then we can run. Just one second.
Self dot.
The recur util. Okay, here also. I need to call it. Like 132, 132. We will submit this also. Yeah, this also 20 milliseconds. It is same because nothing changed right here. So this is the one. Okay, I'll post every. I mean, all these problems into the classroom on the Google Drive. Any doubt? You want me to explain the recursion stack, how it works in case of recursion?
Yeah, Yogesh, that would be helpful.
Yeah, yeah. Because as I told, recursion is easy to write, but we need to visualize it correctly.
Exactly. Yeah, yeah, true.
See, I'll write this 10, 20, 30, then 40, 50, 60, and 100. This should be fine, right?
Yeah.
This problem. So here are see this is my function called in order. I'll call with 100, 10, right? This is the root pointer. This is my first function stack. So what I'm doing is whether I'll check whether this is null or not. This is not null. So what I do, I need to process left first. I'll call in order of 10, 20. I mean in order of root of left. So I call in order of root of left, which is 20. That means this is the left part. I need to call left part, then process. I need to call right part, right? Right part is I've not yet called. Only I'm calling left part. In this 20 also, I'll check whether this 20 is null or not. This is not null. So I need to process left and right, right? So I need to first, I'll go with left. I'll call in order of, this is 30, right?
Yeah.
This is 30. So 30, then this is not null. So what I'll do in order of current of left. This is also I need to call left and then I need to call right. So I'll call in order of null. So when in come what is the base condition? If root equal to null, return, right? I'm not doing anything.
Yeah.
So in this year, I'll check root is equal to null. This guy returned. It comes here. Control comes here. So that means I process the left part. Then what I need to processing the right part is pending. So before processing the right part, when I get the answer from the left part, what I need to do? I need to store the result, right?
Yeah.
So what is the result? 30 is the result. Add 30 to the my output array.
Oh, this is while coming back, right? In that
Yeah,
case.
I came from the left
Okay.
subtree. Before going to the right subtree, I need to add it.
Okay. Okay.
That is what
Understood.
we are doing, right? Here, if you look at this,
Okay.
uh, this is the first one. After I returns from the left subtree, I'm adding here.
Okay. Okay.
Correct, right?
Yeah.
So the left sub function returned. I processed it. That means I added 30, and I need to call the right one. So what I need to do? I need to call in order of root of right. That means 40. Correct, right?
Yeah.
In order of 40 here. So my root is at here. So again, I need to process left and right, right? Just check whether the root is null or not. This guy's root is not null. So what I need to do? I need to call left part, right? In order of root of left. That is in order of root of 30. Correct, no? So again, this 30 you call in order. This is the one. This is not null. So call in order of root of left. That is null. In order of root of null. So I come back. Since it just returns null, then that left part is done. I need to. This is 50, right? Not 30. Sorry, 50, right?
Yeah.
This is 50. So this guy returns. So after this guy returns, I need to process this. That means process 50. Print 50 to the result array.
Okay.
Then you call in order of right. That means what is the 50th right, which is null. I
Yeah.
call in order of null. So this guy also returns. So when this guy returns from the left hand side and right hand side, what should I do? I return to the caller. I also return.
Okay.
Correct, right?
Yeah.
So
Yeah.
I am at 40. So my left processing is done. That means what should I do? I should print this value, right?
Yeah. Yeah. Correct.
Print 40 to the stack. So then I do in order of root of right. That means I call in order of root of right, which is 60. I'm at 60, right?
Yeah.
So now you do, this is not null. You call in order of root of left, which is null. So when this is null, I just return. So I come back to the caller. So when I processing the left subtree, what I should do? I should print it. I print it to the stack and then process the right subtree. Call in order of 60 of right. What is that? That is null. So since if it is null, again this guy returns. So my processing left part is also done, right part is also done. I return back to the caller. So 40, the left part also it returned, right part also returned. I need to return back to the caller, right? So I return back to the caller here. So 30 also, left part is also returned, right part is also returned. So this guy will return back to the caller. So this guy back to the caller. If you look at it, 20 got a return value from its left child. So what should I do? I should process, right? Now
Yeah.
print it to the stack. Sorry, a result array. I printed 20 to the result array. Then what is remaining? I need to process ref towards right hand side. Call in order of 20 of right. But 20 doesn't have right, that is null. So in order of null, if it is null, it just returns. I return back to the caller here. So 20 got result from left side, 20 got result from right hand. That means it processing complete is done, right? So
Yeah.
return back to the caller. So 10 got its result from left subtree. Then we need to process this. So process the result, add 10 to the result array. Then you process right. Then I process right. I call in order of 10, 100. Sorry. So even in order of 100, check whether the root is null or not. This is not null, so I need to process left and right. Process left. That means what is 100 of left, which is again, I'll reuse this, which is a null only, in order of null, right? Maybe I'll take this one here, in order of 100. So here I need to process left. So since this guy is not null, call in order of null. I mean basically current root of left. So since this is null, just return to the caller. Once this guy return, left, I got a return value from left subtree, right? I need to print this now. Print 100 to the result array. Then call in order its right subtree. That means in order of again null. 100 of right is null. This guy also returns back to the caller. So 100 processing is done from left and then right. This guy returns back to the 10. And this 10 is called from my main program. This guy returns. So when I return this, I am doing return of this particular thing. That is present here. Correct, no?
Yeah.
See, again, as I told, it's easy to write, but if we write this state diagram, right, then we can easily visualize properly. This is the key, I think. We should
Yeah. Yeah.
we should write it properly so that we'll understand where control goes and how it comes back from the calling. So, is it clear, or shall I take one more example and run through?
It's clear to me, Yogesh.
Okay. Naveen, it's okay. It's clear. Okay. Uh, then let's jump into the next. We covered pre-order, that is root, left subtree, and then right subtree, which is done. And we covered left subtree, root, and then right subtree. And then the third one is post order. That is a process left subtree first, process right subtree, and then process root. So again, first I'll maybe, since just now we discussed the recursion approach, for this problem also just I'll take some example and I'll explain the recursion tag, how it works. Then we'll jump into the iterative. Okay. Then any idea how we can tweak the existing recursion function to make it work for the post order?
We can just change the position to the end, of that root.
That means we need to cut this and then put it in. Correct, right?
I guess you have stopped presenting, Yogesh.
Oh, is it? Oh, okay.
Yeah, now it's visible.
Yeah, something like this, right?
Yes, yes.
Okay. Yeah, this is perfect. Yeah, this is correct. Maybe I will take this. Hmm. Immediately post. If you look at it, this is considered as a hard problem because it's the iterative way accomplishing post order traversal is not easy as the in order or pre order. I'll explain that. Here, post, post, then self dot taken is equal to t. Then just call post order looping of root then return self dot result. I'll run this. Self. I'll run this. Okay. Solution.
Yogesh, actually, I have to leave. I have some work. Uh,
Okay. Okay. Then we do one thing. Anyway, it's almost close to 11. We'll discuss tomorrow. Is that fine?
yeah, yeah, it's fine.
Yeah. Okay. Just 2 minutes. Okay. Yeah. Fine then. This is all. Maybe tomorrow I'll take about how to write the state diagram, and
Okay,
then we'll discuss the iterative way of solving the
okay,
post order problem, and then we'll discuss some more problems in the
okay,
trees.
okay. Yogesh, one question.
Yeah.
So these, whatever we learned today is related to binary tree, right? Not
Yeah.
binary search tree, right?
No. Binary tree.
Binary search tree is different from binary tree in that case.
Binary search tree is a as good as binary tree, but the
Okay,
constraint in the binary search tree is, say, if the elements in the left subtree are always less than the element of root.
okay, okay,
Okay, if you look at it 100, the left side of the element should, values of the left subtree element should be less than 100. Say here if it is a 80, right? 80 is
okay,
less than 100, it can come here. And
okay,
here if you put 50 and then this is 90, this is
okay,
50, not 50. See again it also falls under this one, right? The
okay.
left subtree value should be less than 80, right subtree value should be less than root. But here, can I put 900 here? No, I cannot, because at this level, binary search tree criteria matches, because 900 is 80. But from this level, it fails, right?
Yeah,
900 is greater than 100. It should be somewhere here.
yeah, yeah, correct.
So from all the levels, recursively, root value should be less than its right subtree values, and then it should be greater than its left subtree values. That criteria should match.
Okay, okay,
That is called as binary search tree.
okay. But the mechanic, this DFS, BFS, and all we can apply on binary search tree also, is it?
Yeah, all these traversals are applicable for any kind of binary tree. It could be binary search tree, it could be plain binary.
Okay, okay, okay. But then the construction of the option what to choose when a particular problem comes, that is a binary tree or binary search tree, it depends on the problem, is it?
Exactly, yeah.
Okay, okay,
See, because if somebody wants to search an element in a binary tree,
okay.
what I can do is I have to go left, I have to go right and search, correct, right?
Yeah,
But
yeah.
in case of binary search tree, just we can make a decision. If the value is greater, go to the right. Don't even go to the left.
Okay, okay,
So that way we can do some decision making,
okay, okay,
because we know how the values are inserted in the binary search tree.
okay. Understood. Okay. Yeah.
Okay. Any doubts? And the assignments folder, right? Still it's empty. I mean, I don't see any solutions. If
Okay.
whenever you get time, try to
Yes,
solve
sir.
assignment problem, so that the coding you will improve your coding skills.
Yeah, sure.
Or yeah, or else maybe we can come back and do assignments one day. I mean, and at least you guys go through the list of problems and just make a list like what problem we should discuss in the next class or something like that. So I can pick that problem and explain.
Okay, okay, okay.
Fine. Okay. Okay, then we'll do one thing. We'll meet tomorrow. We'll
Okay.
cover the remaining problems related to tree.
Okay, okay. Thank you.
Okay, yeah. Thanks, Naveen. Thanks, Ripati, for joining. Thanks, Naveen.
Bye.
Bye.